here in this talk, I will give you an overview about ComIn plugins. ComIn is an abbreviation for ICON Community Interface. Yes, I will keep my presentation short because in the afternoon we have dedicated exercise developing ComIn plugins. So yes, we would see it in practice how we write our own plugins. Okay. So here in this figure, schematically, we see ICON control flow, which starts from model initialization, and then we have several computational components. For example, we have dynamical core as a main component, and we have fast physics processes, and then we have slow physics processes, and at the end, we write outputs and the model stop. Very short. But ICON source code, as in the release for October 2024, it has over 1 million executable Fortran and C code. So it's a huge source code. And when someone from outside the ICON partnership comes and wants to implement a feature in this huge source code, the main question rises, where should my implementation go? And once you are done with your development, it's very difficult to get your branches into to a review process. And if your branch wouldn't merge into a master branch of ICON, then it's very difficult to maintain it because it has to live in a feature branch, which is very challenging to keep it up to date. And yes, it's a tedious process. An alternative approach is to not implement the features directly into the ICON source code, but write plugin for ICON and run your plugins with ICON as a host model. And this is what ICON Community Interface or ComIn is doing. So the ComIn connect the plugins, the third-party modules into ICON as a host model. So yes, the functions or subroutines that you are defined in your plugins are triggered at predefined events in ICON control flow. These predefined events known as entry points. So in this figure that I showed earlier, you can see these lines are dedicated the entry points that is defined in ICON, and your functions in the plugins are triggered in these events. In the plugins, you can also, ComIn also regulate the access and creation of the model variables. So you can access model variables from ICON or create new variable into the ICON list. And it also guarantees a stable interface to the community. It means that the external projects can be relied upon its functionality over time. So it's not like that you develop your plugins and at some point the interface wouldn't work. So ComIn relies on dynamic linking for this plugin mechanism. It means that the shared library built from plugins are loaded into the memory into the at the runtime. In ComIn, we support language interoperability for plugins. So the plugins can be written in Fortran, C, C++, and Python. If you are working with Fortran or C++, you need to build a shared library of your plugin. But in Python plugins, there is no need to do any compilation or building process. So here we want to take a look at the building blocks of a plugin. In this case, we are focusing in Python API, but the overall concept is the same. For example, if you want to write in Fortran or C, the concept remains the same. So here we can see how functions written in the plugin can be registered as a callback. It means that I write this function in my plugins and I registered as a callback using this decorator here to these entry points. So in the icon control flow, when these entry points occur, my function is triggered.
This is like a list of those control points. There are 5 of those.
So I brought the blocks, but yes, your plugins mainly consist of these 4 blocks if you want to implement a feature, but it's not, yes, I didn't write it in an order that you would write that, yes. So here, in the so-called secondary constructor, you create, you can access to a model variable with the read or write access. So you can read a model variable, or you can also write to a variable that you get from ICON. So here, for example, we get, we specify the name and the domain ID. So for which domain we want to access the variable, and then we set some access flags. For example, here I say I want to have a write access to this variable, and I want it to be Halo synchronized after I write it. To it. And this is how we create additional variables to an ICON variable list via our plugins. So here I request to add a new variable with the specific name, and I also can say I want to have this specific variable on which domain. And we can add metadata. We can specify metadata for this variable as well. For example, here in this example, we said that this variable will act as a tracer in ICON. And once we are writing our plugins, we don't need only to access the variables, but we also need some information about ICON setup, computational grids, and the simulation parameters. These data are characterized as a descriptive data structures. These are can be accessed in the plugins at the very earliest stage. And because this information is constant for a specific simulation setup. For example, here in this case, we access the CLON and CLAT from this descriptive data structure that describes the domain, the computational domain. As I mentioned, ComIn is an interface and not a coupler. But the YAG coupler, for example, can be used in your plugins. So here in this example, we use YAG coupler to interpolate a field from ICON unstructured grid to a regular latent long grid. There is a dedicated exercise that we are going to use YAG in our plugin on Friday afternoon, so we can see. Yeah. Yes, now that we learn how we would write our plugin, the next question is how do we enable it? How do we run it with icons? So this process is fairly straightforward. The first thing is that you need to have the right icon binary. It means that it has to be configured with the flag enable ComIn. And once you have your plugin, you can specify it in the Fortran name list, in the ComIn name list, and then you have your plugin activated. So as you can see here, I added one plugin, but the multiple ones can be added. So you can register, 10 to plugins as you want. So here in this example, I brought how we would, for example, use a Python plugin here. So the Python script here is specified as an option because ComIn uses an embedded Python interpreter. This embedded Python interpreter is built when you build ComIn. So it's embedded, it's shipped with ComIn. And here we specify it. I showed this figure to explain the concept of the entry points. So currently we have 41 entry points implemented in ICON. And the new entry points can be added easily. It's just by calling a subroutine in ICON source code here. But an important note is that the granularity of the entry points is above block loop level. It means that only the global variables are exposed from ICON to ComIn plugins. For example, some local buffers in some subroutine in ICON is not exposed, so you cannot access it. And once you are in your plugin, you are in the local partition of the processes. And another important note is that the ICON calls ComIn and not vice versa. It means that in your plugins, you cannot switch off or on some physical or some processes in ICON. So ComIn doesn't control ICON. And if you, for example, want to deactivate some process, you have to do it via Fortran name list, and you cannot do it via your plugin. It's a design decision. Some words about the project history and its status. So the ComIn started as a collaboration between DWD, DLR, DKRZ, and FZ in late 2022. Then in 2023, the project gets mostly done. The first steps was to design a white paper and building a mock-up. And in January 2024, the first version of ComIn also was part of the first ICON open source release. There was a second version release in October 2024. As the naming may suggest, you may think it's a minor release, but it was actually a major release. Many new features were there. And the latest ComIn version is the version 0.3.0, which is released in April this year. And many additional features were also included there. For example, now different data types also supported in the plugins, and some part of the ComIn code was refactored to C++ instead. Here I want to introduce some key resources that if you want to work with the ComIn plugins, it can definitely be very helpful. So the ComIn has its own GitLab project on DKRZ GitLab. It has the source code and the release notes, and there are examples of the plugins in different languages, and also ComIn ships with some tests. ComIn has extensive documentations. So it has a user guide written in the perspective of the plugin developers. It has a design document, and it also has a developer document. So if someone wants to collaborate as a developer, it has very useful information. And it also has a paper published this year, as you can see here. So there's a table of the equivalent interfaces for Fortran API, C API, and Python API. We have practical exercises written in notebooks. It's in the public repository, and it's designed to work smoothly on Levante platform. So if you have access to Levante, you can easily follow along. And another important tool that is shipped with ComIn is the tool called a record and replay tool. It essentially acts as a fake host model. So when you want to develop a plugin, you want to test that with the host model. And in the real world, the host model is ICON. But you can also test your plugin in the development phase with this tool to save the time and energy of submitting ICON jobs to the queuing system. So it makes it easier, and yes, your test can be run with this tool with the C-test functionality. Now, if we want to move on into some applications of some of the plugins that are developed so far. So one example could be the point source plugin, which is in the ComIn repository itself. So this plugin requests a tracer that participates in ICON turbulence and convection scheme, and we add a point source emission to this tracer. So the fun and easy aspects is that we are writing in Python, and we can use the packages available for Python. For example, here we can use KD3 from SciPy to locate the point in the ICON unstructured grid. And this tracer is updated with the tendencies and from convection and turbulence scheme received from ICON. It can easily be extended to a real-world applications, for example, a radioactive point source or a volcano-emitted ash, for example. Another application is streaming the Catalyst API for using in-situ visualization. So ParaView is an open source for visualizing the model data, and the ICON variables can be streamed into ParaView using the Catalyst API specification. And the application of ComIn plugin is that this implementation of the Catalyst API is written into a plugin, as it's not implemented directly into ICON. The last application I want to introduce is, for example, a Python plugin, again written, that extract the ICON grid along the satellite overpass at a different time. So here in this case, it's the AirScare tracks. So the AirScare carries active instrument. It has the information of the vertical profile of the atmosphere. And yes, in this plugin, you can read in a track file, and at each time step in the plugin, you say, okay, this grid point now is in the satellite track, and you extract the vertical profile and write it into an output. And then in this case, this output is fed into the PAMTRA, which is a radiative transfer model, to simulate what would AirScare satellite actually sees from the simulated fields. So now we have an apple-to-apple comparison between what AirScares observe and what we got from our simulation. For example, in this case, it's reflectivity. There is a more advanced version of this plugin is under development, which uses this KD3 search to locate the grid points. It has a more sophisticated MPI offloading, and it has the online PAMTRA integration. So you don't need to write the output and then feed it to PAMTRA. You can online use it in your own plugin. I referenced the GitLab repository for this plugin. Yes, and with the introduction of our ComIn development team at the last of the presentation, I would like to thank you for your attention.